Let's look at these three double angle formulas. They're called double angle formulas because the right-hand side is an expression of alpha. We see alpha, right? Sine alpha, cosine alpha. And the left-hand side, it is an expression of some trigonometric function of 2 alpha. So we call it double angle formula. So how can we calculate this function value using values of functions values at alpha? Okay, so we have the three double angle identities. And you might be curious, why don't we have all 6, right? So, for example, we still have 3 more functions. If you know the tangent, what is the double angle identity of cotangent? What is the double angle identity of secant? What is the double angle identity of cosecant? The reason we do not provide 6 formulas because we have reciprocal properties. So once you know the sine value of 2 alpha, then you can use the reciprocal property to get cosecant of 2 alpha. Once you know the cosine value of 2 alpha, you can find secant of 2 alpha. And with tangent of 2 alpha, right, if we already know how to find tangent to alpha, then you can find cotangent to alpha using reciprocal identities. So we don't need 6. So these 3 formulas are sufficient. With the 3 formulas, let's just have a quick review. So this is sine 2 alpha, which is twice of sine alpha cosine alpha. Cosine 2 alpha, which is cosine square alpha minus sine square alpha. And tangent 2 alpha, which is this fraction, 2 tangent alpha over 1 minus tangent square alpha. So at this moment, recall that we can replace right here between sine and cosine. We want to, for example, use only sine. So use the Pythagorean identity because this identity, then we can replace the cosine alpha, right, using 1 minus sine square alpha. So we can replace it. Then in that case, we get 1 minus twice sine square alpha. So this advantage of this version is that cosine alpha can be written in terms of just sine value of alpha. 1 minus 2 sine square alpha. Or you can replace the sine square alpha. So that is our cosine square alpha, and replace sine square with 1 minus cosine square alpha. This is again by the Pythagorean identity. Then you take out the parentheses. So cosine square alpha minus 1 minus negative means plus cosine square alpha. So you see twice of the cosine square alpha. So we can get twice of the cosine square alpha minus 1. So now we have another version, right, to calculate the cosine 2 alpha. That is, we can use only cosine alpha value to calculate cosine 2 alpha. So we have 3 versions for the double angle formula of cosine. So let's double angle formula for cosine. That is either this version or this second version involving only cosine alpha, or third version involving only sine alpha. So now let's see, the advantage of the second and third is that cosine 2 alpha, of course, we have three different ways of using a double angle. Yeah, actually, we have three different versions of the double angle formula for cosine. So from this version, let's think of the last two versions. If we have cosine, this, which is 2 times cosine square alpha minus 1, we can write this formula in a different way. It's essentially the same formula. How do we write it? We just want to put a square. For example, if I add 1 both sides, that will be cosine 2 alpha, right? If I add 1 both sides, so the left-hand side, if I add 1, the other side will be simply 2 cosine alpha. So after I add 1, I can also divide 2 both sides. So one side divide 2 both sides of the equation. So we can cancel this. And then what happens is that cosine square alpha is solved. See, this formula can be written in a different way. And that means whenever you have a square of alpha, if you use this formula, you see cosine square alpha, we can reduce the power to first power. You see, this is the second power, right? But this is only first power. So it's called power reducing formula. That is, as long as we apply this formula, the cosine square alpha can be reduced. Yeah, the power can be reduced. So let's just write it. So this formula is essentially the same, right? Same formula is just rearranging terms. And then you can see the use of double angle identity by rearranging terms. We can see cosine square alpha can be written as this. Okay, now let's remember this formula. This formula is just cosine square alpha is half 1 plus cosine 2 alpha. Yeah, for whatever alpha. So I just swap. Yeah, I just swap sides, right? Cosine square alpha I put on the left side because my focus is to look at the cosine square alpha. How can I reduce the power? Yeah, so that is how we write a formula. Actually shows the purpose of the formula. That means it can serve the purpose of reducing power. Okay, now let's think of a problem. So if I have a cosine square 15, using that formula, it is, you see, if you have a 15, because it is an identity, right? Alpha is 15, then 1 plus cosine twice of 15. So we just can right now just put 15 here. So you see, if cosine square 15 degrees, it is, but you have a square, and we don't know how to find the cosine 15 because 15 is not a special angle. But if we use the power reducing formula, we can write it as cosine 2 alpha, which is 30 degree. Now between the left hand and right hand side, they are the same thing. So I choose to use the left hand side, right, in order to find out the cosine square of 15 degree. Yeah, so we can continue. We can find 1 plus cosine 30. Cosine 30 is half of square root of 3. And then over 2. So this numerator divided by 2. And this number will be, so 1 divided by 2 plus half of square root of 3 over 2, which is this number. So that is the answer of this problem if you are asked to find cosine square 15 degrees. So this, how do we get this? It's actually through the use of power reducing formula. So this formula we used here. Now, after you use once, then let's try to look at a problem. So what if I have cosine to the fourth power of 15 degrees? Cosine to the fourth power, it is, we know that we can write it as square to a square, because fourth power you can, it's essentially same as the cosine square 15 and to the second power. Yeah, so let's look at this way. Let's handle the square first. Because you see the fourth power, it is a higher power. So, but the second power, immediately we can apply the power reducing formula. So what is the cosine square 15? We just did it, right? Cosine square 15, we can write it as half of 1 plus cosine 30 degrees. With that, if you square again, so of course, if you want to substitute the cosine 30, you already know it is a value. So this cosine 30 degree is a special angle. So you can already evaluate this number. So it is, we can square numerator, which is 2 square, and denominator, which is, so I just square both. Yeah, square numerator and square the denominator. So for a fraction, right, if you raise the fraction to a second power, this is what we're getting now. But we can continue because the numerator, let's keep the 4 here. The numerator, when you square the two quantities, what we do is the first quantity squared plus twice of their product, 2 times 1 times cosine 30 degree, and plus the cosine square 30 degree. Here we used the perfect square formula. Remember, if you have a plus b, this is a perfect square formula. So that is the same as a square plus twice ab plus b squared. So this is the formula we just used, because here, what is a? A is 1. This is a plus b. B is cosine 30. So what we do is this 1, right? The first quantity is squared. Yeah, 1 squared is still 1. And then plus twice their product. So 2 times the first quantity and second quantity, 2 times the product of 1 and cosine 30. So that's, and plus the second quantity squared. So cosine 30 squared. So that is this perfect square formula when a is 1, b is cosine 30. So that's how we get this. Now that's a review of perfect square formula, because we need to remember that result to expand the numerator, right? This is a numerator. Expanded form. Now continue. So we have cosine 30. At this point, you just simply do the evaluations, because cosine at 30-degree angle, we know it's a special angle, so we can just simply reevaluate. Cosine 30 is square root of 3 over 2. So 2 times that number, and cosine 30 square root of 3 over 2. But this number should be squared. So we simply substitute the value of cosine 30, which is square root of 3 over 2. So that we over 4. So now let's simplify this number, because we do not want to write this as an answer. We want to simplify it. So how do we simplify this answer? So continue to write the numerator. You see that this 2 can be canceled, right? The 2 can be canceled. And that one is, so this is a 1 plus square root of 3 plus that square. What is the square of this number? It will be 3 over 4. And the whole numerator divided by 4. So we need to divide every term by 4. So then the final answer is 1 divided by 4 plus the square root of 3 over 4 plus 3 over 4 and another 4, that's 16, 3/16. So the final answer, because let's rewrite, so make it a little, that's the whole thing divided by 4. In this way, you don't need to put a parenthesis, right? That's the whole numerator over 4. Okay, so then we have this final answer. But of course, you can combine 1/4 with 3/16. Yeah, 1/4, if we use the common denominator, you multiply 4, yeah, multiply numerator denominator by 4. So it's 4 over 16 plus 3 over 16. So these two together will be 7 over 16. And then okay, you have one more number. That's the square root of 3 over 4. Okay, so that's the answer for this problem. the problem of evaluating cosine to the fourth power of 15. Yeah, so this problem, you see, we applied twice the power reducing formula. The first time when we applied the power reducing formula is to recognize this fourth power is square of a square. So the square in the parentheses is we apply the power reducing formula. And then we do the expansion of the numerator. And then here you can apply again power reducing formula, but here we do not have to because we know the cosine 30. We can go ahead and do the evaluation now. Yeah, cosine 30 is a value, right? We know. So we can already substitute the value of cosine 30. So actually we used power reducing formula once. Only from here, convert cosine square into this one. That's only once. Power reducing formula. Because here we do not have to. Right here, cosine square, yes, we can apply power reducing formula again, but we don't have to. So we can already go ahead and evaluate, and final answer is this. Now I want to generalize. Suppose we have some angle called theta, and I want to determine the value of fourth power of this cosine theta. Oh, by the way, you realize if I put cosine theta to the fourth power, they're the same. So usually we prefer to put the power, this 4, on top of the cosine. So, but you realize this 4 can be placed on the top of the cosine here, which means the cosine value of theta is raised to the power 4. Okay. So this is any theta. How can we reduce the power? Let's work on this problem and just try to reduce the power using the power reducing formula. By using the power reducing formula. So here, the theta is not necessarily 15 degrees. It can be any measure, right? So it can be anything. So we just, for another angle, for example, any given angle, how do we reduce the power? So we know by our experience, we can write it as a square to a square. So now the inside this part, we can use power reducing formula because cosine square theta can be written as half of 1 plus cosine 2 theta. Yeah, so this is to replace the cosine square theta. So the quantity inside the parentheses, you see the power is reduced. Now the second power is reduced to first power of cosine, right? But cosine of a double angle. So now after this, then we have to do a square. Let's continue. So originally, you see an expression of a false power of cosine theta. Now, after one time application of the power reducing formula, you see this, and then we get this far. So that means it's a second power. Second power, how can we continue? We just do the expansion, very similar to what we did earlier. So let's square the numerator and square the denominator. Square the numerator, cosine 2 theta, square denominator, which is 2. 2 squared is 4. And then what we can do is just keep the 4. And the numerator, you see, again, that perfect square formula. We need to get 1 square, right, plus twice the product, 2 times 1 times cosine 2 theta, plus the cosine 2 theta squared. That's the perfect square formula. So of course, 1 square is still 1. So we get this. And now we can see, basically we have reduced cosine to the fourth power. Now, fourth power has become some function of, to the second power. So we already reduced power, but still we can reduce it to the first power. So how do we reduce? The functions that are already in the first power, we keep it. So 1 over 4, let's each term divided by 4. Let's 2 times cosine 2 theta over 4, which is 2 over 4, which is half, right? Cosine 2 theta. And then the last term is the cosine square 2 theta over 4. Yeah. So we just, each term divided by 4. So we have 3 terms. Then we know what to focus. Focus this one, the last term, because it is still a second power. And we don't want that. We want to reduce everything to the first power. So again, let's use power reducing formula. So right now we keep everything else. We don't worry about 1/4. We don't worry about this second term, which is half of cosine 2 theta. And we only work on the cosine square theta. So this part. Cosine square theta, according to the double angle, power reducing formula, it's 1 plus cosine of twice of this angle, 2 theta. So twice of 2 theta is 4 theta. So let's write cosine 4 theta. So that's all. And then we have achieved our purpose because originally the problem was cosine to the fourth power. Now we have, you see, originally cosine to the fourth power, right? After one time power reducing formula, and we get some expression involving this second power. But now, after one more time of using power reducing formula, because when we see the cosine square, this second power, we don't like it. We want to reduce it again. So here we reduce it again. to this. So now every term, you see cosine, this is first power, right? This is another first power. So we're done. We're done with power reduction. However, the final answer can be organized a little better. So we just combine terms. Let's see if there are any common or like terms. So let's write the numbers. So 1/4 is here, and the second term, half of cosine 2 theta. And then notice that 1/2, 1/4 is actually 1/8, right? Because you multiply the denominators, it's 1/8. 1/8 times this is essentially the same as 1 plus cosine 4 theta. Yeah. So 1/8 times that. That means we should, that the numerator is 1 plus cosine 4 theta. Denominator is actually 1/8 because of 4 and 2. Now we can see that 1/8 by distributing 1/8 to each term. 1/8 times 1 is 1/8. 1/8 times the second term is 1/8 cosine 4 theta. So once we have that, then we can look at the other terms. Half of cosine 2 theta and 1/4. Now it's easier to see, do we have more things to combine? So we just do the expansion first. Mathematically, you always want to put all terms there and see whether there are terms that we can combine. So here, obviously, the numbers, 1/4, 1/8. So we can add together. 1/4, right? 1/4 is 2/8 plus another 8, that's a 3/8. So the numbers combined. And then this one term involving cosine 2 theta. And the other term involving cosine 4 theta. So now you see this is the after we started with this function and we applied power reducing formula, we finally ended at this expression involving 2 theta and 4 theta. The reason is every time you apply the power reducing formula, you have to involve the double angle. Yeah, so that's to notice. When you see this formula, yeah, when you do the power reducing once, you see when the power is reduced, the angle, the double angle is involved here. So once you have some 2 theta expression, and then you again, in your power of this 2 theta, when you want to reduce the power, the angle 2 theta will be doubled again. So that's why we have a final expression involving 2 theta and 4 theta. So after you applied twice the power reducing formula.